to find it, boosting e-commerce search conversions with machine learning at scale by Pino from RIT Boston, who will introduce you a powerful machine learning-based approach to improve the efficiency of finding the relevant items. Please welcome Mr. Pino.
Can you hear me well?
Yes.
Yeah. Thank you for the introduction. As you notice, I changed a little bit the title. This is a mini tutorial about how to do search optimization for e-commerce. And more than find it, I want you to nail it. So we want to understand what are the key technology in order to make a good search optimization for e-commerce. So we are located in Boston, and this is our building. We're on the 4th floor over there. And it's in the financial district in Boston. If you're in the neighborhood, please come and visit. Okay, so this is the outline of my talk. So we'll go with some motivation, of course, and a brief introduction about the traditional information retrieval methods. And most of the talk is going to be about learning to rank models. And then I will have a summary, conclusion, and see what's next. So where are we with e-commerce today? So on the right side of this, you can see this picture where we can take have an understanding of how big is the market for e-commerce. So this is 2016 numbers. So in 2016, we had like a 1.61 billion shoppers buying online, and they generated something like a 1.86 trillion in sales. And if you combine, for example, the 3 big e-commerce companies, like for example Amazon, Otto Group, which is the big one in Germany, and Rakuten, they generated something like $150 billion in revenues. So which is pretty staggering numbers, right? So this is going to be even better probably in 2020 because the total volume of for e-commerce is going to go to $4 trillion. So why is this happening? So the e-commerce is definitely growing faster than a brick and mortar market. So the one thing is happening is about mobile. People are using mobile more and more often to do shopping, especially in Asia. This has been 46% of the shoppers in Asia actually use mobile, in 28% in North America. So also the online catalogs are very big now, so there's a lot of choices for the consumers in competitive prices and products. So although this is a little bit controversial, but so electronic money now is actually gain a little more momentum. So people are more comfortable spending with credit cards or mobile phones to buy online. So here's an opportunity so these transactions here that will generate a humongous amount of data. So there's an opportunity here to use machine learning techniques to even improve, do better on this kind of machinery here. So what does it mean to move from brick and mortar commerce to e-commerce? So it's very simple. So for a physical store, so one of the big differences is actually about the size of the catalog. So for traditional e-commerce, you can have a catalog which is like 250 million products. This is huge, right? And we have 40,000 categories. And the tool that you have available to search in this big amount of data is basically a small window. So your search engine will provide you the little tiny windows up there, and you have to use that tool in order to find your product among those million of products. So the question is, how do we find the most relevant product for a search query? So let's go and take a look at the information retrieval model, the traditional one. So what does it mean to retrieve data from this huge amount of products? So a ranking model is basically a function, f, and it will take 2 arguments. One is for example, the query, and the other one is the document. So it will provide you a ranking or a score, and the score could be high if the product is very relevant. It could be low if the product is not relevant. This will give you the capability to sort the product accordingly to this function. So how does it work in details? So the main concept that the information retrieval uses is this lexical match. So basically we have terms in the query and terms in the documents. If they match together, I mean, that's a good relevance. If they don't, there's not good relevance. And there are different methods for that. So you can see on the right side, so there are, this is a schema for a traditional engine where you can actually index all the documents in the catalog, produce a static representation here, and the search engine will actually score those documents based on the query that you input and produce a result on the right side. So to give you a more concrete example, so this, if you use, for example, a vector model representation, so we can see on the left side a query, like the iPhone 7 case, and then two documents that are retrieved. The one is probably is a case for iPhone 7, and the other one is actually a glass screen. So if you represent those, so for example, if you represent the query with this vector space, which is three-dimensional vector space, you have for each axis, so you have the term. So for the query, we have one instance for iPhone, for 7, and for case. So the other, for the other documents, you match the terms in the description. And for example, document 1, you have 2 matches for iPhone, you have 2 matches for 7, and 2 matches for cases. And for D2, we have 3, 1, and 0. So you can represent that as a vector in that picture. And as you can see, so the query Q is actually closer to document 1 and far away from document 2. So that means it's more relevant for document 1. This is actually what is happening in that case. So what's the problem with this model? So the problem is that so there are very few features you can use. So often what happens is you have to manually tune those features. So there's an expert that actually would go and tweak actually those weights for the features. And you can not include important signals, like for example, user feedback, the popularity of products, or the purchase history, and so on. So on the other side, it's actually very fast and also scalable because it's able to handle million items very easily. So in order to improve on that model, so we introduced what we call learning to rank. So learning to rank means that you learn the ranking from data. So it's a data-driven approach. So directly optimize product rank based on relevance. And we'll go back, we'll talk about relevance more. And then you also handle thousands of features. It is actually robust to noisy data. It can handle personalization. So this is actually the standard people use for like Amazon, eBay, Microsoft, and so on. So what does it mean? So what is relevance basically? So we try to optimize. So it's a very subjective concept. So a document is relevant if it contains the information the user was looking for when you submit the query. And that can be very context dependent. So you can have so subjectivity concerning the context of the query, or the task you try to achieve, or the novelty of the product, and so on. So how do we assign relevance then? So in principle, you should ask, maybe judges, to evaluate. So given a pair of query and document, you can ask them, if it is relevant, is this document relevant for this query? And they can say, well, 1 if it is not relevant, 3 if it is very relevant, and so on. So but this is not really scalable, so it's very expensive, and with the amount of data we have, it's not really possible to do. So what is the alternative? So what if we use the signals from the user behavior? So people interacting with a search engine will produce a number of signals that are very important for to understand what they want. So for instance, clicks, or add something to the cart, or buy something. So those are very important signals. So we can, so what if we replace, so the judgment from, the judges with some information we gather from the user behavior. And this is called the click-through data. So in this case, you definitely get a lot of data because it's very easy to harvest. It's always actually fresh because people are currently, they continuously search for items on the search engine. And they are unbiased, so you don't need, so the judges are not in the picture, so this is completely unbiased. So on the other side, so it could be very noisy. Also, there's a problem with long tail because, for instance, so query with the low number of clicks, they will not receive much attention from the user. But one simple model, is, for example, is to assign a score of 3 for product that are purchased, a score of 2 for product that are added to the shopping cart, and 1 for clicks. So this, of course, is a simplification. It's not a correct representation for relevance. So for instance, here, so imagine you're looking for toasters. So the user actually will definitely look at if you click on number 4, toaster number 4, the user definitely looked at number 1, number 2, and number 3. Maybe he looked at number 5 and 6. But we don't know if he actually look at they definitely didn't look at number 7, 8, and 9. So if you assign relevance 0 to those items, it's not probably correct. But this is actually an approximation, so we'll actually go with it. So now, so we define what is relevance. So we want to know how do we evaluate our ranking measure. So so we need a matrix to see if something is better or worse than two different results in a search engine. So what we use is called normalized and discounted cumulative gain. So imagine you have 10 documents here. So if the top document is the one more relevant, so you have a perfect score, which is 1. So if by chance you have you click on number 2, so the relevance is not on the top, so this matrix will actually drop to 0.6. So as an exponential decay. So if you go on with this, you'll see that the numbers for the NACG will go down quickly. So this metric will actually favor the item on the top and make sure that everything which is relevant will appear in the top 5, 6 in the page. Okay, so this will define the metric. Now, one more thing we need as a recipe is basically what kind of algorithm we need to use in order to learn this from data. So one popular method is called gradient tree boosting. So this is a machine learning approach, which is actually based on tree ensemble. It's very robust because it can handle sparse data, it can handle missing values, it's very robust to outliers, and it's invariant to feature scaling. And it's also available in some interesting implementation, open source implementation that are very scalable as well. So we can use this, for example, as a method for learning. So whenever you pick a machine learning method, of course, you need also to define what is the cost function, what are you trying to optimize. And you can see here, so if you rank in documents, so you can take different approaches in order to consider the pairs, document, and queries. So for example, you can say, okay, I'm just going to look in isolation for the documents. And so this is called pointwise. And in that case, I'm trying to predict the clicks in isolation with the other documents. So then there's another method which is using pairwise. So I'm trying to optimize the pairs where I can definitely see that DI is better than DJ for the query queue. And finally, the best method, of course, is when I consider the whole list altogether, and I try to optimize the full ordering of the documents compared to the query queue. So, to give you a visual understanding of what's going on, so imagine to compare what the pairwise and listwise cost function will do to the ranking. So those are documents, and this is an ideal situation where the top relevant are on the top, on the position 1 and 2. So in this situation, actually, you have a document which is at the bottom. So if you use pairwise, so this will be pushed because of the error is very big between the pairs. It will push a lot. In this case, so when you have the two documents in the middle, so you get a big push in the middle and a smaller push here because the error is smaller. So the listwise actually will push a little bit for this case, and a lot more when you are closer to the top, because this is where it is important to make sure that things are optimized. Sorry. So just to summarize, quick recap. So our recipe includes many things. So we define what's relevance. So user behavior signals is a good proxy for that. We define the metrics, so NDCG. And also we define the machine learning algorithm, which is gradient tree boosting, and the ranking optimization method, which is listwise. And now we have everything to build our model. So what do we do? So here's one way to approximate. So in a real world situation, what do you do? I mean, you don't really replace the whole existing system with a new ranking model, but because there are so many documents, and this is kind of complicated from the computational point of view, so we use the traditional method to do a first screening and produce n documents. Maybe 1 million documents that are probably okay for that query. And then as a second stage, we apply the more sophisticated model, which is called re-ranking in this case. So for example, we take the top 1,000, apply the re-ranking with a very sophisticated algorithm, and then we get the results here. So now in this case, so the difference is we use every single feature we can capture from the existing system. So it's like a kitchen sink. You put in there, because this is very scalable in terms of features, you can use scores from the index, you can use the query structure, you can use the feedback from the user, and so on. So this will become a very powerful model. And, but it's expensive, so it has to be applied to a small number of samples. So we tried this on a real system, Rakuten.com, which is the e-commerce website for the United States from Rakuten. And I can give you an example of results. So this is a query like a 4-inch TV, 40-inch TV, sorry. And you can see there is a missing space. And so the system, which is fully based on lexical matching, will actually fail because it will provide items that are relevant. So they have some correlation with TV, but it's not exactly what the user wants. So the other system actually is able to easily capture the user feedback, because this is a very common query. And it will actually provide the results correctly on the right side. Okay. So in terms of evaluation, so we ran this. We trained the data. We trained the model on many thousands of samples, and we applied we tested it on specific months, and we obtained these results. As you can see, is the model has been trained with different features, parameters. So for this case, this set of parameters provide the best performances. So the NDCG, that is a metric we talked about before, is close to 0.7. And if you remember the definition of NDCG, when you're 0.6, you're already in the top 1 and 2 of the results. So it's pretty good. And this is a boost this provided a boost of 15.58% compared to the baseline of the existing system. So then we ask, but in terms of conversions, how much does this affect the purchases? So we ran a simulation with the new model, and we kind of estimated a 7.5% of conversion rate, which is actually an extremely good number. So that means there's a high correlation between NDCG and conversion, which is a 0.5 basically factor. And now you can see that, so by using all this machine learning, which is actually learning from the data, which is existing in the interaction of the user with the search engine, you can actually add a little gear here that boosts things up and improves the user experience, because the user is going to be able to find what they want quicker, with more relevance. Okay, so this is the first. This is the state of the art, I will say, for information retrieval for e-commerce. But what is next? So what happened to deep neural network for information retrieval? So there is so you can see in different fields a deep neural network have done an impact, a very interesting impact. So speech recognition, for example, 2011, Microsoft introduced an acoustic modeling with DNN, said that created a big improvement in the state of the art. Computer vision, ImageNet, 2013, big improvement in the accuracy of classification. And then natural language is a little bit more fuzzier. So introduction of the embeddings, 2013, CNNs for classification was between 2013 and 2015 and so on. So what about information retrieval? Traditional information retrieval for machine learning has been a little bit slower in the other field. So do we have something for 2017? So apparently there's a lot of work now. So this is not very clear, but there are many papers that have been trying to break the state of the art. We tried some of them, for example, this convolutional network here. They don't perform that well, but very, very recently there was this contribution from Microsoft it's called duet architecture. And this actually mimics very well what we said before. We have this is a ranking function. It has two components, local and distributed, which is mimicking what we said before. So one component is more traditional, an exact match, and the other one is distributed. It's very similar to what we said in two stages we said before. And this one actually is able to improve quite substantially compared to the existing literature. So we get a 32.2 for NDCG, which is quite higher than traditional methods. Okay, so conclusions. So we see that traditional information retrieval methods do not scale well for modern e-commerce, but so we can use user implicit feedback to create models for search queries and document relevance estimation. So learning to rank is actually pretty good for this task, and it produces something like 15.6% over the baseline as improvement. And this improvement is actually translates to conversions with 7.5% increase. And also, so DNNs are coming to the play, so probably in the next few years we'll see more about that. That concludes my talk. Thank you. So we have time for one question, I think.
I have one.
Okay, maybe two.
Well, let's be specific. So NDCG is not a continuous function, and
yes.
Gradient boosting requires derivatives to optimize. So what approximation do you use?
Yeah, actually, it's an excellent question. You're right, it's not a variable. So there's a lambda rank, which is an approximation that I actually use a smoothed version of the NDCG for the derivation.
From Microsoft.
It's from Microsoft, exactly. A good question. We have time for a quick one.
What about personalization?
I'm sorry.
Do you do some personalization? So it's a re-ranking. Does it take an account user profile?
Oh, yes. I have to get the. Yes, good question. So we can actually customize the model for every single user and take into account their personal history, so they can actually personalize to every single user. I think we are over time. All right, thank you.
That's all for this session. Thank you, Tino. Next session will start soon.